and then minus y2 times y1 prime prime. But I want to point out to you guys that what do we know about y1 and y2? What do we know about them? We know they solve this, right? So we know that we can solve like y1 prime prime is equal to like minus a1 y1 prime minus a0 y1 all divided by a sub 2, right? For instance. So I can put that up in here. So I got like, minus a1 y1 prime minus a0 y1 divided by a2, right? And also for the other one, similar thing, minus a1 y2 prime minus a0 y2 divided by, bless you, a2. Right? I know you guys can do this calculation because I said I've put this on tests before and students have done it with success. We're not there yet though. So then what? Does anything cancel? Look at this. We got a y1, y2, and we got a y2, y1. They're both bearing the coefficient of a sub 0 over a sub naught. Excuse me, a sub 0 over a sub 2, right? Those be canceling. And what have we got? Looks like we got a dw dx is equal to minus a1 divided by a2, parentheses y1, y2 prime, minus y2, y1 prime. Can you recognize what that is? It is it's the Wronskian. This is the W. That's W. So what we have then is dw dx is equal to minus a1 over a2 times W. Now here, a1 and a2 are generally functions. They're functions of x, right? But we can solve this. Separate, integrate. What you got? Got yourself a dw over W is equal to minus a1 over a2 dx. Integrate both sides. Do a little bit of algebra, and this gets us to W is equal to, exponential of, the integral of minus a1 over a2 dx. And I suppose you could put a constant here to emphasize that, when we add a constant to in the integral, it gives you a multiplicative constant out front. This formula proves my assertions. See how this works? If the Wronskian is not equal to 0 at one point, that makes this constant non-zero. Therefore, the Wronskian is identically non-zero, which proves it's linearly independent by our previous calculation. On the other hand, if that is 0, that means that the Wronskian is identically equal to 0. And it actually follows then that the solutions are linearly dependent. Although I think technically speaking, I haven't proved that. But this formula I just wrote down for you has a name. It's called Abel's formula or Abel's formula, depending on where you're from, I guess. Now you might say, well, this thing you just did, I mean, it's great and all, but isn't that just for the n equals 2 case, right? How would this calculation go if we were doing, say, 3 functions? How would that look, right? What if there were 4? What if there were n? Well, that is why we have a projector.
So we can utilize this formula instead of doing the determinant to be able to find whether or not it's linearly independent or dependent.
Oh, that is true. You could, good question. Could you calculate this integral to calculate, could you calculate the Wronskian for a solution set? Well, you need to know that there are solutions to the differential equations in order to have the right to calculate the Wronskian in this way. But you're right. If you have solutions to a differential equation, you could calculate Abel's formula to show that they were in fact, well, yeah. I'd say that's true, but it probably has limited applicability. I think the way I was explaining it to you earlier is probably more where we're at. Okay, so check this out, guys. So if you don't mind, I'm going to use the projector to finish the thought today because there's a lot to write out, and there's not a lot to say, but there's a lot to write out. So this is where we got to. This is the theorem I just wrote out. Let me choose the less blinding one. There we go. So this is the theorem I just wrote out, right? Great. The proof in the nth order case, so this is the calculation we just went through together, the n equals 2 case. It turns out that Abel's formula is still true in the n by n, in the nth order case. But the reason for that is a little bit technical, as I shall show you. So here is a formula. This is the formula for the Wronskian of n functions. This is the completely anti-symmetric symbol. This is a stone-cold formula for the determinant of an n by n matrix. When I have that formula, though, that's nice because then I can differentiate it. In differentiating it, I have to attack it with the n-fold product rule, which I do here. And then if you keep differentiating it, you get higher derivatives. But the larger point is that once you have this, you can study it and you can see that you've got like a symmetry and an anti-symmetry and a pair of indices, and as such that certain terms go to 0. And that leaves you with this. And then after a little bit, I plug in the differential equations at that point to replace the particular derivatives with the differential equations, lower order derivatives. And when I do that and plug it in, a bunch of these things go to 0. And I'm able to show that the derivative of the Wronskian for the n by n problem, again, is just minus the ratio of the leading coefficients. Unfortunately here, so the labeling of the coefficients is the opposite way in the notes right now, okay? So this is actually flipped. This is like A0 over A1. It's always the ratio of the leading coefficient to the next to leading coefficients. That's what actually forms Abel's formula. So yeah, it actually ends up being true in the nth order case, but obviously no one would ask you guys to prove that because no one's that crazy.
Did you derive that yourself?
Yes. So, but I love the determinant like a lot in calculus. So it took me a while.
How long?
I don't know. It's a good question.
Like
A couple days probably. Yeah, maybe a couple hours. I can't remember. But it was actually super useful because it turns out that like all of these derivations I was able to use for calculus over in algebra later. But anyway, let me get back to the point here. So a fundamental solution set for a linear differential equation, it's a set of n solutions to the homogeneous problem, which is also linearly independent. All right, that's a fundamental solution set. Our goal next class is going to be constructing fundamental solution sets for the constant coefficient problem. All right. Now, this theorem says that our goal next class is not without hope. If you have an nth order linear differential equation with continuous coefficient functions on an interval I, then there exists a fundamental solution set. So we can do it. And the proof rests on the theorem that I stated earlier today, and I think might still be on the other board over there, which is simply that you can use the existence theorem I have over there And you simply pick the first solution to satisfy this set of initial conditions. So I make it satisfy the initial conditions. The initial position is 1, and the velocity in the acceleration, et cetera, they're all 0. Then my next solution, I fit to the initial conditions. The position's 0, but the velocity's 1, and so forth. And I just keep doing this. And the reason I do this is I choose n solutions so that when I calculate the Wronskian of them, I just get a matrix which is super nice to calculate, namely this so like the determinant of this, it's called the identity matrix. The determinant of the identity matrix is just 1. Okay, so that means then that these functions, y1 through ym, that maybe should be an n. That's a typo. Yeah, I'm sorry about that. Those are n's. So that these n functions are linearly independent because the Wronskian is non-zero at that point, right? Then by Abel's formula, therefore it's non-zero at all points in the interval of consideration. Therefore, they're linearly independent. That's nice. And then here's the big theorem. If we have an nth order linear differential equation with a continuous coefficient function on interval I with fundamental solution set S, any solution of y equals to 0 can be expressed as a linear combination of the fundamental solution set. That is, there exists constants C1 through Cn such that I can write the solution in this form. All right. Now, I'm not saying that the fundamental solution set is unique. By no means. What I'm saying is that if we have a fundamental solution set and we take a linear combination of it, that describes the general possible solution to that homogeneous problem. And if you look at this, the proof of that theorem, inside this proof, there is also an additional proof that there is a unique choice of the constants to form the solution from that fundamental solution set if you're given an initial value problem. Like there's going to be a particular choice of the coefficients C1 through Cn which will reach that set of initial conditions if you have it. And then finally, the general solution to the nth order homogeneous, non-homogeneous linear problem, if we have L of y equals to f as an nth order linear differential equation with continuous coefficient functions on interval I with fundamental solution set such and so forth on I, then any solution of Ly equals to f can be expressed as a linear combination of the fundamental solution set with a second function, let's say y sub p, known as the particular solution, and it has this form. This is what we saw in my example 1 for the nth derivative equal to e to the x. We saw that we had n solutions, and if you go back, you could prove that 1x squared all the way up to x to the n minus 1, those are in fact linearly independent functions. They are. And that my particular solution was actually obtained by the n-fold integration of e to the x, which is kind of boring, but I figured that would be, one less thing to think about today.
There's another typo right there.
Another typo, oh no.
Linear combination.
Where did I do that? Combination? Oh yeah. Yeah, I think I could use a B in there. Yeah. Let's see here. I lost my place. So the claim is that this is a general solution, right? So if I have, the solution like this, right? And if I look at y minus yp, right? Then that gives me L of y minus L of yp, but L of yp was f, and that was assumed to be f. So you get f minus f, which is 0. Thus, yh is y minus yp. That's a solution of homogeneous. So then by the previous theorem, that can be written as a linear combination of fundamental solutions, which then gives us the claimed formula. But anyway, so, and then there's like an example. But next time, I will hopefully show you how we can solve the arbitrary nth order constant coefficient problem. I think you're going to find it is way simpler than you might think it would be.